Take a deep breath and feel the weight of the day begin to dissolve, leaving you light and unburdened. As your body settles into the softness of your bed, imagine yourself drifting upward, moving beyond the clouds and into the velvet embrace of the cosmos. We are traveling now to a place of profound stillness, located in the vast gap between the orbits of Mars and Jupiter. This is the main asteroid belt, a region stretching from about 2.2 to 3.2 astronomical units from the Sun. Here, billions of years of history are written in stone and metal, suspended in a silent, slow-motion dance. You might imagine a crowded field of tumbling rocks, but the reality is much more peaceful. In this immense corridor of space, which spans hundreds of millions of miles, the average distance between any two sizable asteroids is roughly 600,000 miles, over twice the distance between the Earth and the Moon. As you float here, you are surrounded by a magnificent, lonely emptiness that feels both vast and strangely protective. Consider the sheer scale of this celestial graveyard. Despite the millions of individual objects inhabiting this ring, if you were to gather every single asteroid in the belt and pack them together into one mass, they would only equal about 4% of the mass of our moon. It is a fragile, scattered kingdom. Most of what you see is the dust of planets, material that never quite managed to coalesce into a world of its own because of the immense gravitational influence of Jupiter. The gas giant's gravity acted like a cosmic stirrer in keeping these fragments from ever bonding together. As you drift closer to one of these ancient wanderers, you begin to notice the textures of the universe. Reach out in your mind and imagine the surface of a C-type asteroid. These carbonaceous objects are the most common residents here, making up about 75% of the known population. Their surfaces are darker than coal, with an albedo, or reflectivity, between 0.03 and 0.09. If you were to touch this surface, it would feel like frozen soot, gritty, ancient, and cold. This material is among the most primitive in the solar system, containing water-bearing minerals that have remained unchanged for over 4 billion years. Close your eyes within this dream and feel the temperature of the void. Out here, the sun is a brilliant but distant spark, and the rocks are deeply chilled. Surface temperatures in the belt typically hover around -73 degrees Celsius, or roughly -100 degrees Fahrenheit. Yet, there is no wind to bite at you, no air to carry the cold. There is only the sensation of being perfectly suspended in a temperature-less equilibrium, wrapped in the dark insulation of space. In the distance, a great shape looms, the queen of this realm. This is Ceres, the first asteroid ever discovered, spotted by Giuseppe Piazzi on January 1st, 1801. Ceres is so large that it is classified as a dwarf planet, measuring approximately 940 kilometers in diameter. To see it is to see a world in transition. It accounts for about 25% of the total mass of the entire asteroid belt. As you glide over its surface, you see the Occator crater, where mysterious bright spots of sodium carbonate shimmer against the dark regolith-like salt on a black beach. These spots are remnants of briny water that bubbled up from a hidden interior ocean, crystallizing in the vacuum. Imagine the silence of those salt flats, glowing softly under the weak light of a distant sun. Nearby, you might encounter Vesta, the second most massive object in the belt, discovered by Heinrich Olbers in 1807. Vesta is different from the dark, carbon-rich asteroids. It is an S-type, or silicate-based body. Its surface is composed of basaltic rock, much like the cooled lava flows on Earth. Vesta is the brightest asteroid visible from our home planet, occasionally appearing to the naked eye under perfectly dark skies. As you hover near Vesta, you notice a staggering feature at its southern pole, the Rhea Silvia crater. This impact site is 505 kilometers wide, nearly as large as the asteroid itself. In the center of this crater, a central peak rises 22 kilometers into the black sky. This mountain is more than twice the height of Mount Everest, yet it stands in total silence, a monumental testament to a collision that happened 8 billion years ago. Imagine the texture of this mountain, sharp, jagged ridges of ancient stone that have never been softened by rain or wind. It is a landscape of pure geometry and shadow. Consider the rhythmic nature of the belt's movement. While everything seems stationary to your human eyes, every rock is in a constant state of falling around the sun. An asteroid in the middle of the belt takes roughly 3 to 6 Earth years to complete a single orbit. There is a profound patience to this movement. There is no hurry in the asteroid belt. The rocks move at speeds of miles per second, yet the distances are so vast that they appear to hang motionless against the backdrop of the Milky Way. You might notice strange, empty lanes within the belt where almost no asteroids reside. These are the Kirkwood Gaps, named after Daniel Kirkwood, who identified them in 1866. These gaps are caused by orbital resonances with Jupiter. If an asteroid tries to orbit in these specific zones, Jupiter's gravity nudges it repeatedly, like a parent pushing a swing, eventually casting it out of the belt entirely. Feel the invisible pull of gravity as a gentle, guiding hand, organizing the chaos of the rocks into neat, predictable rings. It is the clockwork of the heavens, ticking away in intervals of millions of years. Further out, you might find a rare M-type asteroid, like 16 Psyche. This object is almost entirely made of nickel and iron. If you could see it up close, it would not look like stone, but like the dull, brushed metal of a giant cannonball. Its surface might be smooth in places, reflecting the light of the stars with a metallic glint. Imagine the weight of such a world, a dense, heavy heart of a protoplanet that lost its outer layers in the violent infancy of our solar system. The coldness of the metal would be absolute, a deep, resonant chill that speaks of the heart of a star. As you drift, you begin to sense the rotation of these bodies. Some asteroids, like the small 2001 OE84, spin incredibly fast, completing a rotation in mere minutes. Others turn with a heavy, sluggish grace, taking days to show all their sides to the sun. This rotation creates a subtle shifting play of light and shadow. You see the Terminator line, the boundary between day and night, slowly crawling across the cratered surfaces. In the sunlight, the rocks are a pale, dusty gray or a deep chocolate brown. In the shadow, they disappear completely, leaving only a hole in the stars. The sounds of this place are the sounds of your own breath and the imagined hum of the vacuum. There is a concept in physics called acoustic phonons, the way vibrations travel through a solid lattice. If you were to press your ear against the surface of an asteroid, you might imagine the faint, low-frequency ringing of the rock, a vibration echoing from some distant impact, or the internal settling of the stone. It is a deep, bass note that resonates in your chest, grounding you in the reality of this ancient material. Think of the regolith, the layer of loose, shattered rock and dust that covers almost every asteroid. On Earth, we have soil, enriched by life and water. Here, the regolith is the product of billions of years of space weathering. It is composed of tiny glass beads and microscopic shards created by the constant bombardment of micrometeoroids. This dust is soft, like flour, yet sharp as diamond. Imagine dragging your hand through this dust in the low gravity. It would rise in slow, elegant plumes, hanging in the air for minutes, before settling back down in a lazy, hypnotic curtain. In this part of the solar system, you are far from the warmth of the inner planets, but you are not alone. You are in the company of Pallas and Hygeia. Pallas, in the third largest asteroid, has an orbit that is tilted significantly compared to the rest of the belt, a 34-degree inclination that sends it diving up and down through the plane of the planets. Hygeia, the fourth largest at 430 kilometers across, is nearly a perfect sphere, its shape held together by its own modest gravity. Everywhere you look, there is evidence of the slow dance. There are binary asteroids, where two rocks of similar size orbit one another as they both orbit the Sun, locked in a permanent spinning embrace. About 15% of near-Earth asteroids are thought to be binary systems. This partnership is a beautiful example of balance, a delicate equilibrium where neither rock pulls too hard and neither lets go. As you float here, you realize that you are made of the same elements as these rocks. In the iron in your blood, the calcium in your bones, and the carbon in your cells were all forged in the same stellar furnaces that created these asteroids. This belt is not a cold alien place. It is a pantry of the ingredients of life. When you look at the dark carbon-rich surface of a C-type asteroid, you are looking at the same organic compounds that eventually found their way to Earth, perhaps delivered by these very rocks billions of years ago. The belt is a place of deep time. While the Earth is constantly changing, continents shifting, oceans rising, life evolving, the asteroid belt remains a pristine archive. To be here is to step outside of the frantic pace of human life and enter the slow, rhythmic breathing of the universe. The rocks do not hurry. They do not worry. They simply follow the paths laid out for them by the laws of physics. Paths they have followed for 4.6 billion years. Feel the immense stability of this system. The gravity of the Sun, 93 million miles away from the inner edge of the belt, holds everything in a firm golden grip. The light here is about 1/9 as bright as it is on Earth, casting long, soft shadows that stretch for miles across the cratered plains. The stars above do not twinkle. They are steady, unblinking points of light in a sky so black it feels like velvet. Let the silence of the asteroid belt settle into your bones. It is a silence that is not empty, but full of history and potential. It is the silence of a library, where every rock is a book waiting to be read. As you continue to drift through this slow dance of rock, you feel your own heart rate slow to match the orbital period of these ancient travelers. There is nothing you need to do. There is nowhere you need to go. You are simply a part of the clockwork, a witness to the quiet, enduring beauty of the cosmos. The textures, the temperatures, and the vast, lonely distances are all here to remind you of the scale of existence, a scale that is far too large for stress and just the right size for a deep, dreamless sleep. We will continue our journey through this field of stone, moving deeper into the mechanics of the dance. But for now, just drift. Float in the 600,000-mile gaps. Feel the grit of the regolith and the chill of the nickel iron. You are safe in the vastness. You are home in the stars. As you remain suspended in this quiet theater of stone and shadow, consider the centuries of human curiosity that have reached out to touch these distant worlds. For a long time, the space between Mars and Jupiter was thought to be a simple, empty void. However, in the late 18th century, astronomers began to notice a strange mathematical harmony in the arrangement of the planets. In 1766, a German physicist named Johann Daniel Titius noticed a pattern in the distances of the planets from the Sun, a pattern later popularized by Johann Elert Bode in 1772. This sequence, known as the Titius-Bode law, predicted a missing planet should exist at a distance of approximately 2.8 astronomical units from the Sun. Imagine the anticipation of the early astronomers, staring into the dark with their primitive glass lenses, searching for a ghost. In the year 1800, a group of 24 astronomers, playfully calling themselves the Celestial Police, organized a systematic search for this hidden world. Each member was assigned a specific 15-degree slice of the zodiac to patrol. Picture these individuals in their cold observatories, meticulously sketching the stars night after night, waiting for one point of light to move against the backdrop of the eternal. What they found was not a single great planet, but a multitude of smaller treasures. On the very first night of the 19th century, January 1st, 1801, the Italian monk and astronomer Giuseppe Piazzi discovered Ceres. At first, he thought it was a comet, but its slow circular path revealed it to be something else, because it appeared as a tiny star-like point rather than a disk. The legendary astronomer William Herschel coined the term asteroid in 1802, derived from the Greek word asteroides, meaning star-like. The discovery of Ceres was quickly followed by two Pallas in 1802, found by Heinrich Olbers, then three Juno in 1804, and four Vesta in 1807. For nearly 40 years, these four were considered planets in their own right, listed in textbooks alongside Earth and Mars. It wasn't until 1845, when Carl Henke discovered 5 Astrea, that the floodgates opened. By the 1850s, as dozens of these objects were cataloged, scientists realized they were witnessing not a single broken world, but a vast distributed population of minor planets. Today, we have identified over 1 million individual asteroids, yet they remain as tranquil and spread out as they were when Piazzi first glimpsed Ceres. Consider the asteroid belt as a celestial watchmaker's workshop, filled with the scattered gears and springs of a timepiece that was never fully assembled. This is the metaphor of the belt, a collection of unfinished drafts for a planet that Jupiter's gravity wouldn't allow to form. At this moment, observe the way light interacts with these ancient rocks. Because there is no atmosphere to scatter the sun's rays, the shadows are absolute and ink black. When an asteroid rotates, the transition from day to night is instantaneous. One moment, you are bathed in the pale golden glow of a sun that is 250 million miles away. The next, you are plunged into a darkness so profound, it feels like a physical weight. What's happening now is a subtle phenomenon known as the Yarkovsky effect. First theorized by the Russian civil engineer Ivan Yarkovsky around the year 1900. This process describes how sunlight can actually move a mountain. As an asteroid rotates, its afternoon side, the part that has been baking in the sun, radiates heat back into space as infrared light. This escaping heat acts like a microscopic thruster, a tiny, gentle push that very slowly nudges the asteroid's orbit over millions of years. It is a reminder that in the cosmos, even the weightless touch of light has the power to reshape the paths of giants. Deep within the belt, notice how the asteroids are not just random individuals, but belong to families. This concept was first proposed by the Japanese astronomer Kiyotsugu Hirayama in 1918. He discovered that many asteroids share nearly identical orbital paths and chemical compositions. These Hirayama families, such as the Coronis family or the Eos family, are the shattered remnants of much larger parent bodies that were broken apart by collisions eons ago. Picture a great, crystalline sphere of rock being struck by a wanderer, fracturing into thousands of pieces that continue to travel together through the dark, like a flock of birds following the same invisible current. The color of the light here is unique. Unlike the vibrant blues and greens of Earth, the palette of the belt is subtle and muted. The sunlight, having traveled so far, has lost much of its warmth. It illuminates the C-type asteroids in shades of charcoal and deep umber, while the S-type asteroids reflect a pale stony gray or a dusty olive. There is a quiet dignity in these colors, the colors of deep time and undisturbed mineral. As you observe the slow rotation of a nearby asteroid, you might see the effects of the Yorp effect. This acronym stands for Yarkovsky-O'Keefe-Radzievsky. PADAC, 4 scientists who refined our understanding of how sunlight affects rotation. Sunlight hitting the jagged asymmetrical surfaces of an asteroid can actually cause it to spin faster or slower, or even tilt its axis. Over millions of years, this solar pressure can spin an asteroid so fast that it begins to shed its own dust, or so slowly that it seems to settle into a permanent slumber. It is a dance choreographed by photons, a testament to the patient physics of the void. In 2011 and 2015, the Dawn spacecraft gave us our first intimate look at the 2 most massive residents of this region. It revealed that Vesta is a world of incredible topographical drama, while Ceres is a world of hidden ice. On Ceres, the spacecraft discovered Ahuna Mons, a cryovolcano that stands 4 kilometers high. Instead of molten rock, this volcano once oozed a thick, slushy mix of salt and water ice. Imagine the absolute stillness of a mountain made of frozen brine, standing in a world where the gravity is only 3% of what you feel on Earth. If you were to stand at its base, the peak would disappear into the blackness above, a silent monument to the internal heat that still lingers in these supposedly dead rocks. The belt also hosts the Trojan asteroids, which are not located in the main ring, but are locked into Jupiter's orbit at its L4 and L5 Lagrange points. The first of these, 588 Achilles, was discovered in 1906 by Max Wolf. These asteroids are trapped in a gravitational embrace with the gas giant, eluding or trailing it in its 12-year journey around the Sun. They are the outposts of the belt, guardians of the path, held in place by the perfect balance of centrifugal force and gravity. Notice how the dust of the belt creates a faint ethereal glow, known as the zodiacal light. This is caused by sunlight scattering off microscopic particles of rock and metal that have been ground down by eons of collisions. From Earth, this can sometimes be seen as a ghostly pyramid of light in the pre-dawn or post-sunset sky. Here, in the heart of the belt, it is a soft, omnipresent haze, a fine mist of stardust that reminds you that even the smallest grain of matter is a participant in the solar system's rhythm. At this very moment, consider the immense distance between objects. While we call it a belt, it is more like a vast, sparsely populated ocean. If you were standing on one asteroid, the next nearest neighbor would likely be a tiny, indistinguishable speck, barely brighter than the surrounding stars. This emptiness is not lonely. It is spacious. It is a place where every object has room to breathe, room to exist without friction or noise. The crowded asteroid fields of fiction are replaced here by a majestic, orderly procession. The orbits here are not perfectly circular, but slightly elliptical. 2 Pallas, for instance, has an orbital eccentricity of 0.23, meaning its distance from the Sun varies significantly as it travels. This creates a slow, rhythmic pulsing in the belt structure. As these millions of rocks move, they are constantly performing a delicate adjustment to the gravitational pulls of Mars, Jupiter, and the Sun. It is a multi-body problem being solved in real time by the universe's own logic. As the light of the distant Sun glints off a spinning fragment of nickel iron, think about the timescales involved. A human life is a mere heartbeat compared to the 4.6 billion years these rocks have existed. Many of the surfaces you are visualizing have remained untouched since the dawn of the solar system. The craters you see were formed by impacts that occurred when the Earth was still a molten ball of magma. There is a profound comfort in this permanence. The belt is a sanctuary of stability in a changing universe. Observe the way the stars appear from this vantage point. Without the interference of an atmosphere, they do not flicker. They are steady, piercing needles of light. The Milky Way stretches across the sky with incredible clarity, a river of silver and gold that provides the only weather this region ever sees. The light you see from those stars began its journey decades or centuries ago, just as the rocks beneath you began their journey at the birth of the Sun. You are witnessing the slow, cooling embers of creation. The asteroid belt is not a place of destruction, but a place of preservation. It holds the original recipes for the planets, kept in the cold storage of the void. As you float here, held by the same gravity that guides Ceres and Vesta, feel the ancient history of these rocks merging with your own sense of calm. The history of the belt is the history of our origins, a long, patient story that is still being written in the silent movement of stone. What's happening now is a subtle shift in our journey. As we move from the history of discovery into the very physical essence of these celestial bodies. To understand the scale of the asteroid belt, it helps to relate it to things you might find in your own home. Imagine the Sun as a large front door. In this scale model, the Earth would be about the size of a small nickel, located roughly 20 feet away from that door. The asteroid belt would begin another 25 feet past Earth, stretching out until it reaches nearly 65 feet from the door. Within this wide hallway of space, the largest object, Ceres, would be no bigger than a tiny poppy seed. The rest of the millions of asteroids would be like microscopic flecks of dust, scattered so thinly that you could walk through the entire hallway and never once bump into a single one. So picture this. The total mass of the entire asteroid belt is approximately 3 times 10 to the 21st power kilograms. While that sounds like a staggering number, it is actually only about 1/10,000th the mass of the Earth. It is as if you took the Earth, ground it into a fine powder, and then scattered only a tiny pinch of that powder across the vast gap between Mars and Jupiter. This scarcity is what makes the belt so peaceful. It is not a crowded motorway, but a quiet, lonely gallery of ancient stone. Deep within the structure of these rocks, we find clues to how they were made. Many asteroids, such as 25,143 Itokawa, are not solid boulders, like the granite you might find in a mountain range. Instead, they are what scientists call rubble piles. Itokawa, which was visited by the Hayabusa spacecraft in 2005, has a porosity of about 40%. This means that nearly half of the asteroid's volume is composed of empty space, gaps between the loosely packed fragments of rock and dust. Think of a rubble pile asteroid like a handful of gravel held together only by the weakest of gravitational hugs. If you were to gently push on its surface, the rocks might shift and settle like the beans in a jar, finding a new arrangement in the silence of the void. Notice how the composition of these rocks changes as we move further from the sun. This transition is governed by a concept known as the snow line, or frost line. In the early days of our solar system, about 4.6 billion years ago, there was a specific boundary located at roughly 2.7 astronomical units, right in the middle of the asteroid belt. Inside this line, it was too warm for volatile compounds like water, ammonia, and methane to condense into ice. Outside this line, it was cold enough for them to remain frozen. Because of this, asteroids on the inner edge of the belt are mostly dry, rocky S-types, while those on the outer edge, like 24 Themis, are rich in ice. In April 2010, astronomers using the Infrared Telescope facility in Hawaii confirmed the presence of water ice and organic molecules covering the entire surface of 24 Themis. It is a world perpetually frosted, like a window pane on a midwinter morning. Consider the rhythmic movement of 243 Ida and its tiny companion, Dactyl. Discovered by the Galileo spacecraft in 1993, Dactyl was the first moon ever found orbiting an asteroid. Ida is about 31 miles long, roughly the size of a large city, while Dactyl is only about 1 mile wide, comparable to a small park. Dactyl orbits Ida every 37 hours, a slow and steady loop that has continued for millions of years. This relationship is held together by Ida's gravity, which is so faint that if you were to stand on Ida and throw a baseball, it might never come back down. The bond between these two rocks is a delicate, invisible thread, a testament to the fact that even the smallest objects in the universe seek companionship in the dark. What's happening now is a process called spectroscopy, the primary tool scientists use to understand what these distant worlds are made of. Just as you might recognize a friend's voice by its unique pitch and tone, astronomers recognize minerals by the way they absorb and reflect different wavelengths of light. By looking at the barcodes of light reflected from S-type asteroids, we can identify high concentrations of silicates, such as olivine and pyroxene. These are the same minerals that make up the green sands of Hawaii and the dark lavas of Iceland. When you look at these asteroids, you are looking at the same raw ingredients that form the bedrock beneath your own feet. At this very moment, imagine the history of a specific asteroid called 433 Eros. It was the first near-Earth asteroid to be discovered back in 1898, and later became the first to be orbited by a human spacecraft, the Near Shoemaker, in 2000. Eros is shaped like a giant peanut, measuring about 34 kilometers from end to end. On February 12, 2001, the spacecraft actually performed a controlled landing on the surface of Eros, even though it wasn't designed to land. It settled onto the dusty regolith and continued to transmit data for 2 weeks. This was the first time a human-made object touched the surface of a minor planet, proving that these distant rocks are not just points of light, but physical places with hills, craters, and plains of crushed stone. Scientists discovered that the belt's current state was heavily influenced by a period called the Grand Tack hypothesis. According to this theory, roughly 4.5 billion years ago, Jupiter began to migrate inward toward the Sun, reaching as close as where Mars is today, before Saturn's gravity pulled it back out again. This movement was like a giant snowplow, clearing the road. Jupiter's massive gravity scattered about 99% of the original material in the asteroid belt, leaving behind only the small fraction we see today. Staggering. This cosmic reshuffling explains why the belt is so thin and why Mars is much smaller than the other rocky planets. We are observing the leftovers of a massive architectural reorganization. Think about the density of a metallic M-type asteroid compared to something familiar. While a rubble pile like Itokawa is light and airy, an asteroid like 16 Psyche is as dense as a cast iron skillet. Psyche is approximately 226 kilometers in diameter and is thought to be the exposed core of a protoplanet that was stripped of its rocky mantle by violent collisions billions of years ago. If you were to tap on its surface, it wouldn't crumble like stone. It would resonate with the heavy, dull thud of solid nickel and iron. It is a metallic heart, beating with the cold rhythm of the solar system's birth. Observe the slow, patient orbit of 10 Hygiea, the fourth largest object in the belt, with a diameter of about 430 kilometers. In 2019, observations from the Very Large Telescope in Chile revealed that Hygiea is nearly spherical, which is a requirement for an object to be classified as a dwarf planet. Despite its size, it is incredibly dark, reflecting only about 7% of the light that hits it. Its surface is as dim as a fresh asphalt road on a moonless night. Yet, in that darkness, it maintains a perfect, steady path, completing one orbit around the Sun every 5.59 Earth years. The movement of light through the belt is a slow and steady process. It takes about 13 to 22 minutes for sunlight to travel from the Sun to the various parts of the belt. When you visualize these rocks, you are seeing them as they were nearly 20 minutes ago. And this delay is a reminder of the vastness that separates us. Even the fastest thing in the universe, light, must take its time to cross the comforting void. Picture the collisional lifetime of an asteroid. For a large asteroid like Vesta, which is about 525 kilometers wide, the time between major, life-altering collisions is measured in billions of years. For smaller fragments, only a few meters wide, that lifetime drops to a few million years. Over time, the belt is slowly grinding itself down into finer and finer dust. This is a process of top-down evolution, large worlds becoming smaller, and smaller worlds becoming the zodiacal dust that reflects the sun's glow. It is a slow, inevitable transition from the solid to the ethereal. Consider the Poynting-Robertson effect, a subtle force where solar radiation causes tiny dust particles to lose orbital energy and slowly spiral inward toward the sun. While the large asteroids are held in place by gravity, the finest dust is constantly being vacuumed out of the belt over millions of years. The belt is breathing, losing its finest particles to the sun, while creating new ones through the slow-motion collisions of its larger residents. Notice how the temperature varies as an asteroid spins. Because there is no air to hold the heat, the side facing away from the sun can drop to minus 190 degrees Celsius. However, the dark, carbon-rich surfaces of C-type asteroids are excellent at absorbing heat, meaning their noon can be relatively warm compared to the surrounding void. This constant thermal cycling causes the rocks to expand and contract, a process called thermal fatigue that slowly cracks the stones over millions of years. Even without wind or rain, the rocks are slowly being weathered by the light itself. As you contemplate these facts, feel the connection between the familiar and the cosmic. The same physics that governs the way gravel settles in a driveway or the way frost forms on your freezer door is at work 300 million miles away. The asteroid belt is not a chaotic mess. It is a highly organized, predictable, and quiet laboratory of nature. You are safe within this knowledge, held by the same laws that keep Dactyl in its orbit around Ida. Allow the rhythmic, mechanical beauty of these orbits to guide you into a state of deeper stillness. The slow dance of rock continues, with or without us. Ease, a permanent and peaceful fixture of the universe we call home. At this very moment, as you drift further into the stillness, consider that the asteroid belt is not just a distant ring of debris, but a celestial attic filled with the original blueprints of our existence. Scientists discovered that these rocks are more than just cold mineral. They are time capsules, holding the secrets of how you came to be. Think of the water that flows through your body, the very hydration that cools your skin and fills your cells. Much of that water may have been delivered to a young, dry Earth billions of years ago by asteroids from the outer regions of the belt. By comparing the deuterium to hydrogen ratios in Earth's oceans with the water found in carbonaceous chondrite meteorites, researchers have found a remarkable match. This suggests that the same stones you are visualizing tonight were the vessels that carried the life-giving oceans of our world across the void. Deep within the composition of these ancient wanderers, we find the chemical precursors to life itself. In 1969, a meteorite known as the Murchison meteorite fell in Victoria, Australia. When researchers analyzed this fragment of a C-type asteroid, they discovered it contained over 70 different amino acids, including the building blocks that make up the proteins in your own muscles and organs. Picture this. The very ingredients for a heartbeat and a thought were forged in the cold, dark silence of the belt, long before the Earth was even a solid world. There is a profound connection between the iron in your blood and the metallic heart of an asteroid, like 16 Psyche. You are not a separate entity from the cosmos. You are a localized expression of the materials that have been dancing in this ring for eons. Notice how our modern curiosity has led us back to these seeds of life. On June 27, 2018, the Japanese spacecraft Hayabusa 2 arrived at a diamond-shaped asteroid named 162173 Ryugu. This small world, only about 900 meters in diameter, is a primitive carbonaceous object. When the spacecraft returned 5.4 grams of Ryugu soil to Earth in 2020, the analysis was groundbreaking. Scientists discovered uracil, one of the 4 nucleobases in RNA, and vitamin B3, or niacin, tucked inside the dust. This confirms that the complex organic molecules necessary for biology are naturally occurring throughout the asteroid belt. You might feel a sense of belonging as you realize that the chemistry of your own mind is written in the dust of these distant rocks. Consider the asteroid 101955 Bennu, a small dark world that was the focus of NASA's OSIRIS-REx mission. Bennu is roughly 490 meters across, about the height of the Empire State Building, and it is older than the Earth itself. As the spacecraft orbited Bennu, it found evidence of magnetite and carbonate minerals that only form in the presence of liquid water. This implies that the parent body Bennu broke away from billions of years ago must have once had flowing water within its interior. At this very moment, somewhere in the belt, there are rocks that still harbor frozen pockets of that ancient, primordial moisture. It is a quiet, frozen memory of a time when the solar system was a much warmer, a more active place. The relationship between the asteroid belt and the Earth is one of both creation and protection. picture the massive influence of Jupiter, which acts as a cosmic shepherd for these rocks. With a mass 318 times that of the Earth, Jupiter's immense gravitational field prevents most of the asteroids from wandering into the inner solar system. While we often think of asteroids as a threat, Jupiter ensures that the belt remains a stable, orderly ring. Scientists discovered that without Jupiter's presence, the Earth would likely be bombarded by large impacts much more frequently, potentially preventing life from ever gaining a foothold. You can rest in the knowledge that you are living in a remarkably well-organized system, shielded by the very giants that shaped the belt's architecture. What's happening now in the field of planetary defense is a testament to our growing understanding of this dance. On September 26, 2022, a spacecraft called DART, the Double Asteroid Redirection Test, purposely collided with a tiny moonlet named Dimorphos. This moonlet, which is only 160 meters wide, orbits a larger asteroid called 65,803 Didymos. The impact was a success, changing Dimorphos's orbital period by 32 minutes. This was the first time humanity intentionally altered the motion of a celestial body. It reminds us that we are no longer passive observers of the cosmos. We are becoming active participants in the preservation of our world, learning to gently nudge the stones of the belt to ensure our continued safety. Think of the Sentry system, a highly automated collision monitoring program managed by NASA's Jet Propulsion Laboratory. It continuously scans a catalog of over 30,000 near-Earth asteroids, NEAs, to predict potential impacts for the next 100 years. At this very moment, the system is watching thousands of points of light, calculating their trajectories with microscopic precision. This vigilance is not a source of worry, but a source of peace. It means that the comforting void is well mapped and understood. We know the paths of these wanderers as well as we know the streets of our own neighborhoods. Scientists discovered that the asteroid belt might one day become a resource for the future of our species. An asteroid like 16 Psyche is estimated to contain enough nickel and iron to be worth $10 quadrillion in Earth's economy. Beyond the metallic wealth, asteroids are rich in rare earth elements and platinum group metals. But perhaps more importantly, the water ice found in asteroids could be used to create fuel and air for future explorers. Imagine a future where these ancient rocks serve as filling stations for travelers moving toward the outer planets. The belt, which was once a barrier to our understanding, is slowly becoming a bridge to the rest of the galaxy. Consider the concept of prebiotic chemistry as you visualize the dark, carbon-rich surfaces of these objects. The asteroid belt is like a vast slow cooker where simple molecules have been simmering under the influence of solar radiation and cosmic rays for billions of years. This process has produced complex hydrocarbons that coat the regolith of many asteroids. When you think about the smell of space, astronauts often describe it as seared steak or hot metal. This scent is actually the result of polycyclic aromatic hydrocarbons, the same kinds of molecules found in the belt. The universe has a physical sensory presence that is surprisingly familiar, a scent of home that drifts across the vacuum. At this very moment, the ESA's Hera mission is preparing to return to the Didymos system to study the crater left by DART. This mission will provide a detailed autopsy of an asteroid impact, helping us understand the internal structure of these bodies. Whether they are solid metal or loose rubble piles, each discovery helps us feel more connected to the mechanical reality of the solar system. We are learning the weight, the texture, and the strength of the stones that make up our neighborhood. Picture the long-term implications of our relationship with the belt. For 4.6 billion years, these rocks have been the silent witnesses to every volcanic eruption, every ice age, and every evolutionary leap on Earth. They are the elders of our system. When you look at an asteroid, you are looking at a piece of the universe that has remained unchanged since before the first breath was ever drawn on our planet. This permanence is a soothing thought. In a world of rapid change and fleeting moments, the asteroid belt is a constant, a rhythmic pulse that has beaten since the dawn of time and will continue long after we are gone. Notice the way your own rhythm has slowed as we explore these vast timescales. The Late Heavy Bombardment, a period of intense asteroid activity about 4 billion years ago, here may have been the very event that seeded the Earth with its organic riches. We are the children of that ancient chaos, now living in a time of profound celestial order. The slow dance of rock is the choreography of our own origins. Every orbit of Ceres, every rotation of Vesta, and every nudge from Jupiter is a part of the grand mechanism that allows you to lie here in peace tonight. As we move toward the next phase of our journey, hold on to the feeling of being part of this cosmic lineage. You are made of the same carbon found on Ryugu and the same iron found on Psyche. The asteroid belt is not a distant, cold place. It is the source of the very materials that allow you to dream. The universe is not something you are looking at. It is something you are a part of. The silence of the void is the silence of your own deep history, a quiet, protective space where you can let go and simply exist. The rocks will continue their slow, patient circuits around the sun, and you can continue your own journey into the soft, welcoming dark of sleep. What's happening now is a deepening of our sensory exploration as we move beyond the visual and into the subtle, hidden physicalities of this immense stretch of stone. Imagine the sound of the asteroid belt. In the traditional sense, there is no sound in a vacuum, as there are no air molecules to carry a wave. Yet, if you were to press your forehead against the cold surface of an asteroid like 21 Lutetia, which was visited by the Rosetta spacecraft in 2010, you might feel a different kind of music. Scientists discovered that asteroids can resonate with the kinetic energy of distant impacts or the internal shifting of rubble. This is a low-frequency vibration, a deep, rhythmic hum that travels through the rock itself. It is a tectonic lullaby, the sound of a world that is ancient, solid, and incredibly dense. Lutetia has a density of about 3,400 kilograms per cubic meter, making it far more substantial than the loose rubble piles we've encountered. Notice the texture of the ground beneath your imagined touch. Most asteroids are shrouded in a layer of nanophase iron. This is a result of space weathering, where the relentless bombardment of solar wind and micrometeoroids breaks down minerals on the surface, leaving behind microscopic particles of pure iron. This dust acts as a cosmic velvet, softening the jagged edges of the craters. On an asteroid like 253 Matilda, which the Near spacecraft flew past in 1997, the surface is so dark and porous that it resembles a giant piece of charcoal. Matilda is over 50% empty space, a cavernous structure of shadows where light is swallowed almost entirely. Imagine the sensation of your hand sinking inches into this light, powdery soot. It would feel weightless, a dry and ghostly silt that has never known the weight of water. At this very moment, consider the scent of the void. While space itself is a vacuum, the asteroid belt is rich in polycyclic aromatic hydrocarbons, or PAHs. These are complex organic molecules that, when brought into a pressurized environment like a spacecraft, have a distinct aroma. Astronauts have described this scent as a mixture of seared steak, hot metal, and the bitter smoke of a welding torch. Picture this. The asteroid belt has a fragrance, a sharp and metallic perfume that speaks of high-energy chemistry and the forging of worlds. It is the scent of the solar system's workshop, a raw and honest smell that lingers in the silence. Deep within the belt, the colors are more diverse than they first appear. While most of the rocks are charcoal or slate, there are extraordinary exceptions. Consider 624 Hector, a massive D-type asteroid that is shaped like a giant bone. Hector is strikingly reddish-brown. This color comes from a thick coating of tholins, complex organic solids formed by the ultraviolet irradiation of simple compounds like methane. This deep, rusty crimson is the color of the outer solar system, a hue that hints at the icy depths from which Hector may have originated. Picture this. Some asteroids even behave like comets. In January 2019, astronomers noticed something peculiar about the asteroid 6478 Gault. It had grown two long, thin tails of dust, stretching hundreds of thousands of miles into space. This wasn't because it was melting, but because it was spinning so fast due to the Yorp effect that it began to physically disintegrate, shedding its outer layers like a cosmic dandelion, releasing its seeds. What's happening now is a transformation, where a solid rock becomes a soft, ethereal streak of light, a temporary bridge between the world of stone and the world of gas. Notice how the temperature fluctuates in this shadow-filled corridor. The average temperature of an asteroid in the belt is approximately minus 73 degrees Celsius. But this is a fluctuating reality. On an S-type asteroid, like 7 Iris, which is about 199 kilometers wide, the lack of an atmosphere means there is no insolation. The side facing the sun might be a brisk minus 20, while the side in shadow plunges to a terrifying minus 150. This creates a thermal pulse as the asteroid rotates. This pulse is a gentle rhythmic expansion and contraction of the rock, a slow breathing of the mineral body that occurs over hours or days. Scientists discovered that some asteroids are actually triple systems. Take 87 Sylvia, a large asteroid discovered in 1866. In 2001 and 2005, astronomers found two moons orbiting it, named Romulus and Remus. Sylvia is a rubble pile that is so loosely held together, it is essentially a collection of rocks traveling in formation. Imagine standing on Romulus and watching Sylvia rotate, a massive, spinning mountain of gravel, while the smaller Remus glides silently in the distance. It is a slow-motion ballet, performed in a dark, silent theater with no audience, a perfect display of gravitational choreography. Consider the albedo, or the reflectivity, of these worlds. Most asteroids are as dark as fresh asphalt, but E-type asteroids, such as 44 Nyssa, are outliers. Nyssa is composed largely of a mineral called enstatite and has an albedo of 0.55, meaning it reflects more than half the sunlight that hits it. If you were near Nyssa, it would glow with a brilliant pearlescent light, appearing like a polished gemstone against the velvet blackness. It is a rare, bright spark in a kingdom of shadow, a reminder that the belt is not a uniform place, but a collection of unique personalities. What's happening now is a connection between the belt and your own world. Scientists discovered that a specific group of meteorites, called Hay-D meteorites, Howardites, Eucrites, and Diogenites, all originated from a single location. the asteroid 4 Vesta. About 1 out of every 20 meteorites found on Earth is actually a piece of Vesta, blasted off its surface by a massive collision a billion years ago. Think of the rocks you may have seen in a museum or even found in a field. Those stones are literal ambassadors from the belt, fragments of a distant world that you can touch with your own hands. The slow dance of rock is not just out there. Its participants are here, among us. Notice the movement of 133P/Elst Pizarro, a main belt comet. It orbits in the middle of the asteroid belt, yet it periodically develops a tail, showing that it still harbors a heart of ice. This object is a bridge between two worlds, a reminder that the boundary between an asteroid and a comet is often just a matter of how much ice is hidden beneath the dust. It is like a secret garden buried under a layer of sand, waiting for the sun's warmth to reveal its true nature. At this very moment, imagine the Geminids, one of the most reliable meteor showers on Earth. This shower is unique because its parent body is not a comet, but an asteroid named 3200 Phaethon. Phaethon is a rock comet, an asteroid that gets so close to the sun that its surface cracks and crumbles from the heat, leaving a trail of debris. When you see a shooting star in December, you are seeing the dust of an asteroid burning up in our atmosphere. You are witnessing the final act of a journey that began millions of miles away, a brilliant, fiery conclusion to a very long and silent dance. Scientists discovered that the asteroid 511 Davida is one of the largest irregular objects in the belt, with dimensions of roughly 357 by 282 kilometers. Because it is so massive, its gravity is almost strong enough to pull it into a sphere, but its internal strength holds it in a jagged oblong shape. This creates a strange gravitational field, where down changes direction depending on where you stand. Imagine walking across Davida. The horizon would tilt and sway, and your weight would shift with every step. It is a world where the laws of physics are the same, but the experience of them is wonderfully alien. Consider the metaphor of the asteroid belt as a cosmic hourglass. Each collision, each nudge from Jupiter, and each photon of sunlight is a grain of sand falling through the neck of the glass. Over billions of years, the large rocks are ground down into dust, and that dust is eventually swept away by the solar wind. But this hourglass is so vast that the process will take billions more years to complete. We are living in a moment of exquisite balance, where the stones are still large enough to be worlds, and the dust is still thick enough to glow in the twilight. Deep within your mind, feel the stillness of this environment. The asteroid belt is a place where nothing is ever in a hurry. The asteroid 3122 Florence, a trinary system with 2 moons, takes nearly 1,600 days to complete a single circuit around the sun. There is a profound patience in this orbit. It does not seek a destination. It simply honors the curve of space-time. This is the ultimate form of rest. To be in constant motion, yet never feel the strain of travel. As you contemplate the textures of the regolith, the scent of the hydrocarbons, and the red and silver light of the distant rocks, feel your own body becoming as still as one Ceres. Ceres is 940 kilometers across, yet it is tiny compared to the moon, accounting for only 1/3 of its diameter. This smallness is part of the charm of the belt. It is a kingdom of miniatures, a gallery of small, precious things. The universe is providing a space for you to let go. The slow dance of rock is a mechanism of peace, a clock that never needs winding, and a song that never ends. Allow the cold, metallic heart of the belt to ground you, and let the soft iron dust of the regolith cushion your thoughts. You are drifting in a safe, predictable, and beautiful corridor of history. The rocks will be there when you wake, continuing their patient orbits. And for now, you can simply fade into the silence of their ancient rhythmic company. What is happening now is the beginning of a gradual, quiet return, a slow migration of the mind from the silent debris of the asteroid belt back toward the warmth of your own presence. As we prepare to conclude this journey, consider the step-by-step process of how this field of stone came to be. It began 4.6 billion years ago within the solar nebula, a swirling disk of gas and dust. At first, tiny grains of mineral collided at low speeds, sticking together through simple electrostatic forces. Over thousands of years, these grains grew into planetesimals, small building blocks of worlds. While these blocks merged to form the inner rocky planets, the material in the belt was caught in a gravitational tug-of-war. Scientists discovered that the primary reason a planet never formed here was the influence of Jupiter. At specific locations called the Kirkwood Gaps, for instance, at the 3-to-1 resonance where an object orbits 3 times for every 1 orbit of Jupiter, the gas giant's gravity repeatedly nudged the rocks, increasing their velocities until they collided too hard to stick, shattering instead of merging. Observe the way these bodies evolved internally over millions of years. On a world like 4 Vesta, the heat from the decay of short-lived radioactive isotopes, such as aluminum-26, caused the entire asteroid to melt. This led to a process called differentiation. Step by step, the heavier iron and nickel sank to the center, while the lighter silicate rocks rose to the surface. Today, Vesta possesses a distinct internal structure, including a metallic core with a radius of approximately 110 kilometers, a rocky mantle, and a basaltic crust. This is the same fundamental process that organized the Earth. When you think of the bedrock beneath your home, you are connecting with a geologic sequence that was mirrored in the heart of Vesta billions of years ago. Picture the slow mechanical process of space weathering that continues even as you lie still. Every second, microscopic particles called micrometeoroids strike the surfaces of asteroids at speeds exceeding 10 kilometers per second. These tiny impacts do not create large craters, but they vaporize a microscopic amount of mineral. This vapor then settles back onto the surface, forming nanophase iron particles, grains of pure iron, only a few nanometers wide. Over millions of years, and this process gradually darkens the asteroid's surface, a phenomenon known as optical maturing. This slow, invisible rain of dust is the universe's way of aging the stone, turning the bright gray of fresh rock into the deep, dark charcoal of the ancient void. Consider the rhythmic life cycle of a binary asteroid system. About 15% of the asteroids in the belt are thought to have a companion. The process of forming these pairs often begins with the Yorp effect, the gentle pressure of sunlight. As the sun heats the uneven surface of a small asteroid, the escaping infrared radiation creates a tiny amount of torque. Step by step, over hundreds of thousands of years, this torque causes the asteroid to spin faster and faster. Eventually, the centrifugal force becomes so great that the asteroid reaches its critical spin rate, causing loose material to lift off the equator and coalesce into a small moon. This is how the system of 65,803 Didymos and its moon Dimorphos likely formed, a slow-motion birth where a single world becomes 2, held together by the invisible threads of their own gravity. What's happening now is a realization of the deep chemistry that connects the belt to your own life. Scientists discovered that the carbonaceous chondrite meteorites, which originate from C-type asteroids like 10 Hygiea, contain up to 20% water by weight, locked within their mineral structures. This water is isotopic evidence of the early solar system's composition. Furthermore, these rocks carry nucleobases like adenine and guanine, the very components of your DNA. The carbon in your heart, the nitrogen in your lungs, and the phosphorus in your bones were all participants in this slow dance of rock before the Earth had even cooled. You are a living vessel for the materials of the asteroid belt, a complex arrangement of stardust that has found a way to dream. Notice how the light in the belt is fading now in your mind's eye. The sun is 2.8 times further from the belt than it is from Earth, meaning the solar energy reaching these rocks is only about 12% of what we experience. This dim, cool light creates a perpetual twilight, a soft and heavy atmosphere of shadow. As we move away from the orbits of Ceres and Pallas, the slow dance of rock continues without us. The billion-year-old process of the Poynting-Robertson effect is still at work, as solar radiation causes the finest dust particles to lose orbital energy and spiral inward, inch by inch, over millennia. It is a cosmic cleaning process, a quiet and inevitable movement toward the sun. At this very moment, surrender to the feeling of weightlessness that these asteroids know so well. On a small asteroid like 25,143 Itokawa, the gravity is so weak, about 1/100,000th of Earth's, that your own heartbeat would be enough to move your body. Allow that sense of total buoyancy to fill your limbs. Your muscles no longer need to hold you up. The Earth's gravity is a soft, supportive bed, not a weight. You are as suspended and safe as a fragment of nickel iron in the comforting void. As the visual of the asteroid belt dissolves, replace the cold of space with the internal warmth of your own breath. The journey through the millions of miles of the belt was a journey toward stillness. The mechanical precision of the orbits, the steady rotation of the planetoids, and the patient grinding of the dust are all reflections of the order and peace that exist within you. You are part of a system that has functioned perfectly for billions of years. There is no chaos here, only the long-term logic of physics and the quiet persistence of matter. Begin to sense the rhythm of your own body as a smaller version of the solar system's pulse. Your breathing is an orbit, slow, circular, and reliable. Your heart is a steady rotation, a beat that has been echoed by the ticking of the cosmic clock since the first planetesimals collided. The slow dance of rock is now the slow dance of your own rest. Permit your mind to settle into the deep, a dark regolith of sleep. This is a place where time has no meaning, where the 4 billion-year history of a rock is no different than the silence of a single night. You are grounded, you are supported, you are made of the very same elements that glint in the light of the distant sun. As the last images of Vesta's craters and Ceres' salt flats fade away, embrace the darkness not as an empty space, but as a protective blanket. The universe is vast, but it is also intimate. The iron in your blood is the same iron that resides in the core of 16 Psyche. The water in your cells is the same water that frost coats 24 Themis. You are home. You are returning to the source of all things, to the quiet state of being that existed before the first stars ignited. Surrender to the silence. Surrender to the heavy, warm pull of sleep. In the rocks will continue their dance. The gravity will hold the rings in place. The sun will remain a distant golden guardian. You are safe in the clockwork of the heavens. Rest now. Your journey is complete. The void is not empty. It is full of peace. The stone is not cold. It is steady. The dance is not over. It is just beginning a new, quieter movement. Allow the following thoughts to guide you into the final shadows. My body is as still as the heart of Ceres. My mind is as clear as the vacuum between the stars. I am held by the same laws that guide the planets. I am a part of the ancient, enduring story of the stars. Every breath I take is a peaceful orbit. Every moment of rest is a billion years of history. I am weightless. I am warm. I am stardust. I am at peace. I am home. The shadows are soft. The dark is a sanctuary. The asteroid belt remains in its slow, magnificent procession, and you remain in your deep, restorative slumber. The stars are watching, steady and unblinking, as you drift into the final, perfect quiet. Good night.